Hello everyone. Welcome to the fourth recorded lecture in C202 fluid mechanics flow in pipe section. Last lecture we discussed about laminar flow. In this lecture we will discuss about turbulent flow in pipe. If you remember, in laminar flow, the velocity or flow of field fluctuate only with time. That means once velocity profile is fully developed, we have same velocity to the direction of flow. But in contrast, in turbulent flow, in turbulent flow, what we can see is the turbulent flow field fluctuates both in time and space. That means if we yes, if our average velocity is v, if it is v, we can see sometime velocity, there is a fluctuation for velocity. We call that is u dash. You can see you can maintain average velocity at u bar. If the average velocity is say u bar in this figure, we have some fluctuations. Okay. Therefore, at any time, if the velocity at any time, let's say at this point, if you consider this point, the velocity u equal u bar plus this fluctuation. Okay. Then due to these fluctuations, is the turbulent effect. In addition, this we will the fluid particle experience the additional shear stress. We will discuss that in next slide. See, this is suppose this is a small section or part of the fluid inside the pipe. This particle indicates the fluid particles. But what happened here in the case of laminar flow? In the case of laminar flow, what happened? Always the fluid particles moves in one direction. There is no fluctuation, right? That's why during our in last lecture when we derive some equation, we assume the shear stress or frictional effect is only due to the laminar effect. That's why we use the Newton's viscous law to derive some equations. But in the case of turbulent flow, right, this is very important because it fluctuates with time and space. Look at this particle, the blue color particle. If at when say at time equal time 0, if it is at this point, maybe in another point, it can it is not necessary to move in the forward direction, the say x direction. It can move like this and move like this. Okay, t equal this is say t1. This is at t2. Okay, then likewise this particle can move like this. Okay, then now what happened? Because there is a disturbance to the flow from one particle to other particle. That's why we said in the case of turbulent flow, not like in the laminar flow, we can have the flow experience additional shear stresses. Okay, right. Therefore, in the case of turbulent flow, right, look at this is our pipe. Say this is pipe. I will change the color. Say this is our sorry Which color is better? Yeah. If this is the pipe wall, right? You pipe wall, right? Say we learn the tau, say stress at the any kind of flow. It is 0 at the center and increase linearly toward the pipe end, pipe wall. That tau in total tau or CI stress at the given place in the turbulent flow, there are two components. One is the CI stress due to viscous effect or lamina effect. Okay. Then another term, additional CI stress is developed as you observe in the previous slide. That is due to tau r is due to turbulent effect. We call that is the Reynolds stress or turbulent CI stress. Okay, the tau v we call that is viscous CI stress. Okay, then the important thing in the then according to the experimental, we can prove that this tau r component equal minus r u dash v dash. What is this u dash? That fluctuation in this is in x direction or flow direction. This is for other direction because it can fluctuate in radial direction too, right? Then we know that viscous shear stress from viscous shear law, tau v equal mu times du by dy. Okay. Remember, in turbulent flow, therefore, the total CI stress, there are two components. One is due to viscous effect, another one is due to turbulent effect. If you consider the fluid layers around the near the pipe wall, the tau r is tau v is significant. Okay, at the near the pipe wall, tau r, almost all the CI stress is mainly due to this viscous effect. Okay, then when we go from pipe wall to toward the pipe axis, we can see the effect of tau r become significant. The effect of tau v decreases. Okay, then at the pipe wall, we know tau naught boundary CI stress, so wall CI stress almost equal to almost due to the lamina effect or viscous CI effect, right? Okay, then the total CI stress at any given point, we can write tau v, that means mu times du by dy minus rho u dash v dash. Okay, why this become minus? Because if we take the product of u dash and v dash, that is a positive value, then this become positive. Okay, therefore we know the mu equals rho times mu. Mu means kinematic viscosity. I explained that you in the very first lecture, I think. Then tau total CI stress, we can write rho nu du by dy minus rho u dash v dash. Okay, right. That is this is the what I explain in word, right? That means near the pipe wall, viscous shear stress is significant. When we go from pipe wall to toward the center of the pipe, the contribution of tau r is significant. Maybe there is a 1 point. Okay, and after this point, all total shear stress is due to the tau r. Okay, the effect of tau e is negligible. If you refer to my lecture note, which I uploaded to the fields, you can see many more information about this shear stress distributions. Okay, right. Then the past research on turbulence flows, then they hypothesized that the turbulent eddies would have the same diffusive or mixing effect. Therefore, they hypothesized an eddy viscosity closer to the closer for the Reynolds momentum flux. That means we can write earlier we see tau r equal minus rho u dash u v dash. Then this u dash v dash component can be replaced by nu t times du by dy. This nu t we define as eddy viscosity. Okay. Sorry, I forgot to tell that in the case of turbulent flows, the many theories and fundamentals were developed based on the both theoretical and experimental results, because the turbulent flows are difficult to analyze or write equation. Therefore, most of the theories were developed based on the experimental data. Then for near wall flow, the Prandtl, in the research, they suggested that the turbulent eddy viscosity, that means this nu t can be written as nu t equal L squared du by dy. What is this L squared? L squared is called mixing length. L squared is called mixing length. The physical meaning of that, the length that say that there is a turbulent flow fluid particle, the length that fluid particle moves before it collides or hits with another fluid particle. We call that is L, mixing length, right? Okay. Then he suggested that this nu t or eddy viscosity can be written as L squared times du by dy. Okay. Then again, for experiment, we can see that this mixed length L is equal k times y. This k is called one Komanam constant. Usually that value is 0.4. Okay. Why? We know it is the distance to the given point. It is a distance to the given point measured from the pipe wall. Okay, right. Then we can write. You can see tau r equal rho nu t times du by dy. Instead of nu t, we can write, right? I will write here. This tau r equal rho nu t. Instead of nu t, now we can write L squared. L squared, right? Du by dy. dy. The right. Then L squared du by dy. Yes. Times this du by dy. Du by right dy. right? Then according to this equation, we can substitute L for this L squared. Then we will get tau r equal rho density k squared y squared du by dy times squared. Right, all the derivations of these equations I have given in the uploaded lecture note. Please refer that if you have any unclear point. Okay. Then we can see we learn two equations in the very first lecture, right? The shear stress, the shear velocity u star equal tau naught over rho. This can be applied for laminar and turbulent flow, both flows. Then from this we can write tau is equal, right? Tau maybe for tau naught equal rho times u star square from this equation. Okay. Then we will consider this. Further we consider a fluid layer. It is far enough from the wall to allow for the Reynolds shear stress, that means turbulent shear stress to completely dominate the viscous shear stress. In that case, the tau, right, is equal rho nu t du by dy. We learned this in previous slide. Then we can write the both are tau. Then equation A equal equation B, right? Then rho u star squared equal rho time k squared y squared this term. Okay. Then from that we can yeah, from here we can derive this one. Then if you simplify this, the rho to rho cancel, then take square root, then we will get u star equal k y times du by dy. Okay. If you integrate, then we can rearrange this equation into this form, right? If you integrate both sides, we will get, right? We will get u over u star equal 1 over k ln y plus c. This clearly indicates that this is the velocity equation for velocity profile, the fundamental equation for velocity profile of turbulent flow in a pipe. This clearly explains the velocity profile of a turbulent flow has a logarithmic velocity distribution. Okay, now let's try to find the constant as we did in the laminar flow. So this is the velocity profile, right? Then we know, right, the u is the velocity at the distance r, u star is the shear velocity, then u divided by u star has a finite value. It should have a value, right? But if you apply our no slip boundary condition, we know that when y equal 0, that means at the pi pole u equal 0. Okay, then this constant, okay, this become that in that time this u over u star becomes infinite. Okay, infinitely. So then what we do is we assume, since anyhow we have to find the value of this constant c, then we assume we define very small length y naught. The u becomes 0 at a very small length from the pipe wall. We call that is y naught. Okay, y naught. Then we define u becomes 0 at y equal y naught. Okay, right. Then we can write equation at we can use no slip boundary condition. Okay, then we can write at y equal y naught at y equal y naught u equals 0. Then this value of constant we will get minus 1 over k ln y naught. If you have any unclear thing, you please refer lecture note, printed lecture note uploaded. All these steps are there. Okay, then we can write, right? We can write u over u naught u star equal 1 over k ln y naught minus value of c equal minus 1 over k ln y naught. This is right, right? Not y naught. This is y. 1 over k ln y minus 1 over k ln y naught. From that, we can derive this equation. Okay. Therefore, for a right, what is the value of k? Value of k equal one common coefficient equal 0.4. You learned previously 0.4. If you substitute 0.4 there instead of k, you will get u over u star equal 1 over 0.4 equal 2.5 ln y over y naught. If you convert that into log 10, it's become 5.75 log y over y naught. Okay, this is the velocity profile, the equation for velocity profile for the turbulent flow. As I explained previous slide, you can see the distribution of this top figure, the distribution of a turbulent flow has a log distribution. That means the flow velocity profile for the turbulent flow is fairly flat across the center location and drop rapidly extremely close to the pipe pole. That is how that, as we all know, the log varies. Right. Then we know that because in the previous equation, we have y naught term, right? Because we don't know exactly what is the value. But then we can modify the equation. We saw that in next slide. We can modify. Okay. We know that this velocity turbulent flow velocity profile, it is a logarithm distribution, right? At the pipe axis. At pipe axis, it's almost flat, right? Then du by dy become 0, right? There is no gradient. Gradient becomes 0. That means we can find maximum velocity at the center line at y equal r naught. At y equal r naught, the u become u equal u max. Okay, u equal u max. Right. Again, therefore, we can write our basic equation. Right. You know equation u over u star equal 2.5 ln, right, y over y naught. Right. The previous slide we learned that. Then by substituting, we know that u become u max at y equal r naught. Therefore, we can write this equation. Okay, right. Then we know our, yeah, that is this equation is this one, right? Then say this is one, equation number one. I will clear all the drawings. Say this is equation number one. Okay, this is equation number two, right? Then from 1 minus 2, okay, from 1 minus 2, you can get u max minus u divided by u star equal 2.5 r naught over y, or 5.75 log 10 r naught over y. Why, what is important in this equation is, in this equation, say this is our general equation, the first we derive, but in this equation we have y naught term, but here we don't have y naught term. Therefore, this equation is very useful when we consider the velocity distribution of turbulent flows. Right. Again, for you remember for laminar flow, we derive V average flow equal u max divided by 2, right? U max divided by 2. But if we do same thing, we can see that the relationship between maximum velocity of the turbulent flow and the average velocity V is u max minus V over u star equal 3.75. You please remember this equation. Okay, then from this equation we can write the average velocity V equal u max time maximum velocity times maximum velocity minus 3.75 times u star, right? That is this equation. Okay, then previously you learned that the u star equal V times f square root of f over 8. Therefore, if we modify this equation into this equation too, but you don't have to remember all those equations. You must remember this equation, then you can derive this, then remember this equation, then you can come to this. Okay. Then we can prove that in the laminar flow, in the turbulent flow, right? In the turbulent flow, the velocity profile we have like log distribution like this. Say this is the average velocity v, okay. Then we can find average velocity v at a distance of y equal d over 9 this by. Okay, we can prove this. Maybe in the discussion class we will prove this. Till now, believe me, in the turbulent flow, the u equal v, that means average velocity, we can always see at a distance y equal d over 9. Okay, d over 9. Then this is our general equation. Then we can substitute v there instead of u. Then y become d over 9. Okay. Then we know previous slide we learned v over u star equal 8 over f square root of 8 over f. If you substitute this term there, you will get this equation. Okay. Further, we know this is 8 is the value. Then further, if you simplify this, we can reduce or we can simplify this equation into this equation. Okay. This equation is called the 1 over square root of f equals 0.88 ln d over 9 y naught or equal in log 10 term 0.2.03 log 10 d over 9 y naught. We call this equation the friction equation in turbulent flow. Okay. Therefore, the friction factor, you see, f is a function of d and y naught in this case. Okay, it's also a function of Reynolds number. We will learn that later. Right. Then, if you remember, laminar flow, we had parabolic, velocity profile, and Reynolds friction factor F is only 64 divided by Reynolds number. Okay. Then, but if you consider this turbulent flow, the turbulent flow, this velocity profile is has a logarithm variation. That means around the pipe axis, it's almost flat, and it drastically reduces the velocity near the pipe pole. Okay. Right. That is the difference. Right. That is all about turbulent flow, but I know that this section is very difficult to teach as in online mode. Then during the discussion class, we still did not started. Uh, I have given a nice lecture note to you. Please refer that. And during the discussion, we will online sessions. We will discuss further if you have any doubt. Okay. With that, I would like to summarize today's lecture. We discuss, right? The turbulent flow. Due to turbulence effect, there is a additional shear stress. Additional shear stress, we call that is turbulence shear stress or Reynolds shear stress. Then the total shear stress has a two component, tau equal tau V, viscous shear effect plus tau R, Reynolds shear stress. Okay. Near the pipe wall, this tau V is dominant. Okay. Then toward the center of the pipe wall, the tau R is dominant. Okay. Then later we show that the velocity profile of turbulent flow has a log variation. Okay. Then we derive this equation. Okay. We can find velocity at any given point using this equation. Okay. Then further we learn that the relationship between average velocity and the maximum velocity and the shear velocity for the turbulent flow. Then finally, right, we derive the friction equation for the turbulent flow. Right. Then right. With that, I have given you two exercises. Okay. The first exercise is, you can see a liquid, the density 850 kilograms cubic meters per second. The mu dynamic viscosity is 0.015 kilopascal second. Flows in a pipe diameter 300 with mean velocity 4 meters per second, and the frictional head loss over 4 meter loss of 4 meter over 75 length of the pipe. Okay, you have to calculate, probably this flow is a turbulent flow. You have to calculate tau tau 50, Umax, right, and U50. Okay, these are the answers. You try yourself. You try yourself for this exercise. We will have discussion on this. Then I have given another exercise to you. Okay, this is again turbulent flow. Okay, you have to find uh, velocity, Umax, tau naught, U20 values, right? I will first you work out yourself, then I will upload the answers to the online learning system, right? Then this is one of the hardest system section in this pipe flow section. Hope you will go through this several times and try to understand and simultaneously refer my lecture note. Right. With that, I would like to wind up this online recording. If you have any question, doubt, please you can ask through Wheels or through email. Thank you.